Let's make this water steamy. I don't know how many people. Just out of curiosity, oh, how many people own a rice cooker? Yeah, they're fantastic. If you don't own a rice cooker or don't know what a rice cooker is, basically the idea is, and look, it kind of looks like a crock pot a little bit. This one looks like it's an electronic one. The idea is that you have this little basin of water that you fill up, and this thing boils water. That's what it really does. You put a lid on it, you put your rice in there, and the rice doesn't sit in the water. The rice cooks in the steam that evaporates off the water. And if you can lock this thing down like a pressure cooker, you basically can get your steam up to like 130 degrees, 150 degrees. And because the steam is hotter than the water ever could be, because water boils at 100 degrees, you can flash cook your food. It's brilliant. It's great. Not only does it make the cooking faster and more even, but people say that it keeps the nutrients in your food better. So you can steam cook your broccoli this way if you want to. Now, my brother-in-law, he owns one of these things, but he also works in a professional kitchen. And what he says is that honestly, when he's working in a professional kitchen, they don't have like a whole bunch of rice cookers sitting around. They have large pots, and they have a boiling reservoir in the bottom of the pot, and they'll have baskets that they insert into the pots, and they have little lids on top of them, and they'll have like a whole bunch of these things going so that they can quickly cook the food for the customers. This is a very common thing for food, okay? Food sciences. So it's something that could show up in your home, and if you don't have a rice cooker, you can get one. But we're going to go through the calculations, okay? So I got this rice cooker. I want to put 2 kilograms of water. Of course, we know that that means 2 liters of water. So this is maybe more on the scale of my brother-in-law's commercial kitchen, because we probably don't have a 2-liter rice cooker sitting at home in our kitchens, but this is a big one. And I want to recognize that if I'm going to heat up this water, the water is going to follow an energy graph that looks like the energy graph we've talked about before. Now, I always start off with my minus 20. Is the water that I put into my rice cooker ever going to be minus 20? No, you're not putting in really cold ice cubes into a rice cooker. So I'm going to draw the whole graph, and I want you guys to help me out with figuring out what parts of this graph I'm going to be transitioning as I prepare to cook my rice. 130 is where the cooking tops out here. We've seen that value before.
I'm going to freeze my rice before.
All right, so I've got my temperature in degrees Celsius. I've got my energy in joules, and I'm going to pour more and more energy into my water as my rice cooker heats up. But where on my graph am I going to start this process? Okay, so I'm going to trace with my pen. Can you guys as a group tell me when to stop? Okay, this is like Dora the Explorer or something like that. Okay, like
No.
I'm the map. I'm the map. All right, so starting here, you guys tell me when to stop.
Stop.
All right, y'all missed it. Let's try it again.
You're moving too fast.
Okay, going. Stop. You're going to put in water that's 0 degrees Celsius? No. That's like ice cubes. I'm still loading ice cubes into my rice cooker.
Stop.
All right.
So like 50.
Dora says stop. Look at that.
I go a little higher.
Now, according to the word problem, it says that we're going to start at 80 degrees Celsius. So maybe our scale is a little bit off. We could have been closer to the 100, but I'll say there. Okay, that's 80. So this is my 80 degrees. Okay. Now, can you guys tell me when I'm going to stop my cooking process? Read the whole problem. I'm the map. On the map. Stop. All right. No swiping. All right. So we get up to 130 degrees. Okay.
That's kind of broken down. So bad.
Now, as I break this down, you're going to have to do 3 calculations. Look, this calculation here is calculation 1. This calculation here, this is calculation 2. And then this calculation here is calculation 3. Because as I traverse this graph, I have to traverse 3 parts of the graph. Step up, go sideways, step up again. That's the energies here, okay? So calculation number 1 is delta EH for the water, when it's water, is equal to the mass of the water times the heat capacity of water times the delta T for the water. Now, don't forget, delta T water has hidden within it T2 for water minus T1 for water, right? That's kind of hidden under the hood. of the delta T. Calculation number 2 is going to be heat of vaporization for the water, which is just going to be LV times the mass of the water. No change in temperature because we're just changing state in that transition. And then calculation number 3, delta EH for the steam. This is once that water is evaporated out of the lower basin, so now it's going to be doing its cooking job on the rice, is going to be equal to the mass of the steam times the heat capacity of steam and the delta T for the steam. Again, remember, that delta T for steam is T2 for steam minus T1 for steam. It's hidden in there, okay? And eventually somebody realizes, like, oh my gosh, this thing is water the whole time. And when it's water, it has one heat capacity. When it's transitioning, there's another coefficient. And when it becomes steam, maybe you didn't realize this yet or not, maybe you didn't look at the tables from yesterday's homework, it has a different heat capacity. Turns out that steam has a different heat capacity than water does, okay? That's something that if I don't highlight it, people will mess up when they do their homework calculations. And they'll be like, why am I getting it wrong? That's why. Because when it's in water form, it takes a different amount of energy to raise water 1 degree Celsius than when it's in steam form. Okay, and that's just a physical observation of the world in which we live. Now we could look these things up, and I've already looked them up. 4.18 times 10 to the power of 3 joules per kilogram degree Celsius is the heat capacity for water. Again, you have reference tables for this in your workbooks and in your textbook. The heat capacity for steam is equal to 2.00 times 10 to the power of 2 joules per kilogram degree Celsius. Hey, and you know, the nice thing about this is it takes a lot of energy to boil water, but once you get water to turn into steam, notice that it takes like less than a tenth as much energy to make super hot steam, which is another reason to cook with steam. You know, like it actually is a good cooking material. And we can talk about how that might relate to gas laws and things in chemistry class, but that's not what we're talking about today, right? And the latent heat of vaporization for water is 2.268 times 10 to the power of 6. Oh my gosh, that's a big coefficient, joules per kilogram. So vaporization is a real energy hog, like just getting it to transition, which again highlights why a watched pot never boils. Because boy, you got to put in a ton of energy to boil that water, like to get it to that vaporization, to get it to start steaming away. Especially if you really are a cook, anybody ever tried to like make gravy and they put too much water in, and you have to thicken the gravy by evaporating the water away? It's called reducing it. And if you're trying to produce a reduction, you got to get rid of all that water. This energy issue here, this coefficient being to the power of 10 to the power of 6, means that reducing a watery gravy takes forever, which is why people cheat and put like cornstarch in and stuff. You know, like it actually is a whole issue. So whether you're making gravy or whether you're trying to thicken up a curry, it takes forever to get rid of that water. Like it's a real issue for people cooking. I only bring this up because it's something that you actually encounter in your day-to-day life. Hopefully somebody in your house has made you cook the dinner every once in a while. Anyway, if I want to figure out how much energy it takes, the total energy it takes to get this steam up to the point where I can cook my rice is going to be, well, the sum of those three energies, delta EHW plus delta VW, delta EHS for steam. We're going to add them all up. Now, I am really in love with just doing it all in one shebang, but I also know that I have a few people in the class that feel more comfortable with breaking it up. So let's do it that way. Let's try and chunk this one out. So delta EHW is equal to MW CW delta TW. Expand it out, MW CW. Delta TW, remember I said is T2W minus T1W. I'm only saying that because we got to really hash out which values we're going to put in here. So 2 kilograms of water, we said back at the beginning. 2 kilograms of water times the heat capacity of water, 4.18 times 10 to the power of 3 joules per kilogram degrees Celsius, times T2W minus T1W. I want to take a look at this graph for a second. What's T2W? What's the final temperature of the water? Yes, sir.
130 or 100?
It's either 130 or 100. Which one is it?
100.
100. Look, the water stops being water at the 100 mark, right? So T2 for water, 100 degrees Celsius. T1 for water was 80 degrees Celsius, yeah. Do my calculations. Anybody get it?
167,200.
167200. I heard it. Yep. 167,200 joules. That's how much energy I got there. Calculation 2. Calculation 2 is a little quicker. Delta EVW, the amount of energy I'm pouring into this thing by vaporization. Now I'm throwing in a delta there. Really, technically there shouldn't be a delta because nothing in this equation is actually changing. Notice that there's no like M2 minus N1 or LV minus L1. The reason I'm putting that delta in there is to remind us that there's a change in energy happening, okay? Really, technically, maybe it doesn't go there. But I'm putting it in to remind us that we're changing how much energy is in there. We sub in the values 2.268 times 10 to the power of 6 joules per kilogram times 2 kilograms. And I calculated this is like 4 million, 4.5 million. If you're having a hard time seeing that it's the million, I'll throw in some commas just so you can kind of see it there. It's a big number. And we could write it in scientific notation, but I don't want to round things off prematurely. I mean, really, in my heart, I'd like to do this as one mega equation, but I'm chunking it out because somebody told me just like within the past 2 days that they like to see things chunked out. So that's why I'm doing it, okay? So calculation 3, delta EHS is equal to MSCS delta TS. Now, I didn't really acknowledge this, but if the water was 2 kilograms, then when it was changing state, it was 2 kilograms. We never think about steam as having a mass of 2 kilograms, but you know that you can, if no particles got out, if this is a truly contained system, wouldn't the steam also be 2 kilograms? You have 2 kilograms of steam. People don't think about steam as having like, a weightiness to it, but of course it's made out of particles, and that's what kilograms are. It's a measure of the mass of the particles. So 2 kilograms times the heat capacity of steam, which was 2.00 times 10 to the power of 2 joules per kilogram degree Celsius. Now, T2 minus T1. I didn't expand out my delta T this time. What's T2 for the steam? Let's go back up to our graph. Final temperature for the steam is 130, yeah. Initial temperature for the steam was 100. Look, 130 is the final, 100 is the initial for steam, okay? Got to be specific about the temperature that the state was at. So final temperature, 130 degrees Celsius. Initial temperature for steam, 100 degrees Celsius. I kind of regret that I left out a line where I expanded the delta T, but it would have looked very much like this one, right? Delta T, but for steam. Okay. All right, so I do my math, and I end up getting 12,000 joules. Look at that. Doesn't that look like just a drop in the bucket energy-wise compared to the other ones? Nothing to superheat steam. You can make really hot steam. This is a great cooking strategy. And I totally get that it's not something that everybody has. If you eat a lot of rice, this is a good thing to have in the house, okay? Growing up, I ate a lot of rice. I ate a lot of potatoes growing up. That's my mom and dad's cooking. My mom's from British descent. I married an Indo-Caribbean person, and the Indian and the Caribbean in my family makes a lot of rice, let me tell you, okay? That's our main carb, I would say, even more than pasta for sure. Anyway, when I calculate the total energy, we're just summing up these values. Essentially, we're taking this expression down here, and we've done all the legwork. We're adding up all these values. 167,200 joules plus 4,536,000 joules. Oh, I don't even have enough space here. Plus 12,000 joules. I do all that, and I end up getting 4,715,200 joules. And if you're having a hard time separating out the numbers, I'll throw in some commas there to separate the clusters of 3. Does that sound about right? And then we switched over to scientific notation for the sig figs. I think way back when, all the way back up here, 3, and actually we bottomed out at 1 decimal place too, even. But 4.72 times 10 to the power of 1, 2, 3. Oh, 1, 2, 3, 4,
Six.
5, 6. Oh, that would have been easy. That's exactly where I put a comma. Joules. Okay? And we can have a little therefore statement. And for full marks, I would say, therefore, it takes 4.72 times 10 to the power of 6 joules to cook my rice. Actually, not just to cook the rice, but to get the steam up to temperature, right? Here's a challenge. How much energy would it take to boil a swimming pool? We're not going to do that. What would you need to know, though? If you needed to know how much energy it was going to take to boil a swimming pool, what would you first need to know?
The amount of water in it.
There you go. Yeah, you need to know. Probably you'd talk about the volume of the water. Then you'd probably take that water and turn it into a mass because you need to know the density of water, right? That seems reasonable. Then I suppose all you need to know is the heat capacity of water.
But you already do know.
What else would you need to know? Yeah? Yeah, the starting temperature of water. So T1W for the water. And then what would the T2W be for the water?
100 degrees.
100-degree water. Now that's if it's pure water. We know that
There's chlorine.
We know that there's chlorine in there, or if it's a salt pool, it's got some other ionic compound dissolved in it, and so the boiling temperature is probably going to be a little below 100. So remember, 100 is only for pure water. This is kind of like I love these Fermi problems. If you ever see a Fermi problem in the notes, think it out. Think about what you would have to do. Fermi problems are nice ones where you're not really expecting to get a definitive answer. It's just training your brain to think in this way. They're a classic way to train our brains to think in this way. I challenge you. Try some of the Fermi problems every once in a while. Not everybody's looking at them.